Okay, so hope recording is fine. So let's continue from where we left off. Before discussing more properties of ideal gases which can be derived from StatMech, let's take a small detour and discuss something else, especially the expression, uh, the way we calculated the expression for the volume of a three-dimensional sphere in momentum space. So let's discuss phase space volume calculation, and the energy till now what we have been discussing is the energy of the system is constant, and that is P1 square plus P2 square plus P3 square and so on and so forth till P3n, if there are n particles, and I'm assuming that the mass of all particles are the same. Yeah, and this equation corresponds to the surface of a sphere. Okay, and actually the energy of the system was considered, I mean, though I keep saying that it's the energy is fixed at E, but actually the energy of the system uh, is to be considered between E and E plus dE. And this dE is related to the precision in the energy measurement. So it's, you are really interested. So the system is actually between energy E and E plus dE, because that depends upon the precision with which you can calculate, you can measure the energy. And so, this is the surface of a sphere, but actually the system is between this in because the energy is between E and E plus dE, it's actually exploring microstates, momentum microstates. I mean, talking about the momentum degrees of freedom, which are between two spheres with surfaces E and E plus dE, and dE by E is much less than 1. Okay, so it's a very thin shell. So basically, it can uh, explore momentum, any value of momentum within that thin, uh, I mean, momentum, such that the energy is between E plus dE. So the phase space volume that we should be calculating is actually the volume of that shell. Okay, so because there can be many different values of energy and corresponding microstates possible. So actually we should be calculating omega, the total, the phase space volume between E plus dE Vn and omega EV and N. Okay, uh, that is the volume of the spherical shell, as I was telling you. Uh, and note that the real space, that is, the particles are moving in real space like x, y, z, and the momentum space is decoupled in the integral, because the omega, um, the phase space volume, and as I had written down, is proportional to V. V is the volume of the box. Volume, I mean, it might be a sphere or a cubic box. It really doesn't matter. Each particle can explore all the ranges of x, y, and z as defined by the constraint of the box. So hence I have written that V to the power n, and that is decoupled from the momentum integral, where here I am written the energy should be between E and E plus dE, right? So it's that shell, and the particles are actually on the surface of this sphere. I mean, the momentum. I'm talking about the momentum degrees of freedom, right? So just to remind you, um, if you have to calculate the momentum of the the volume of that shell, we can also write it down as 4 pi. I mean, if we are doing it in suppose 3D, then we'll extrapolate the same idea to a three-dimensional space. So the volume of a shell, spherical shell in 3D, is 4 pi r squared dr. Where does this 4 pi r square come from? It is rate of change of volume with dr into dr, right? So that's how you can calculate the volume of a shell, right? But if you are in 3n dimensions, then instead of 4 pi, you will be getting some other number, c dash, right? C dash, which is different from C, because this prefactor in volume is 4 pi by 3. When you take the derivative, you get 4 pi, right? So I'm writing C dash because when I was using volume, yeah, we had a prefactor of C3n, but here it is dash. And r to the power n minus 1 into dr, where r was, just to remind you, was 2me, right? It's basically coming. So if you write this as r square, right? So you basically, in terms of momentum, you get the equation of a sphere, a surface of a sphere, right? So here you would get 3n minus 1. And I mean, if you want to draw a parallel with this, then it's dtr. And this was the volume of the sphere in 3 dimensions, as we had calculated in the last class. This, to remind yourselves if you have forgotten, right? Into dr, equivalent to this, right? Now, but when we are working with entropy, right? When we are calculating statistical thermodynamic quantity and relating it, we are not working with this. We are working with log, right? And so what I want to say is, if you take the derivative of this, this will be, I mean, you'll be getting c dash r to the power 3n minus 1 dr. And when you take the log of it, you will get log c dash plus 3n minus 1 into ln of 2me plus ln dE, right? If you're talking of volume of the shell, and the system is confined within the volume of a shell. Now, this definitely is a different value of the constant. So basically, here you have 3n. If you are talking about volume of the shell, this is definitely different. But this 3n minus 1, n is an extremely large number. Extreme, because statistical physics is valid for when n is large, not for when n is small. So one can as well write 3n minus 1 equal to 3n. And moreover, here you have ln 2me, 3n into ln 2me, and dE is much smaller than E. So when you take its ln, the contribution to entropy is negligible compared to this term. So we can as well drop this term. Moreover, though the C dash is definitely different from C3n, when you calculate quantities like the temperature or the pressure, there should be appropriate. So this is a partial derivative with appropriate things kept constant. This C dash is going to drop out, right? When you take derivatives with respect to energy, or you take a derivative with respect to volume. So it's not going to matter at all. Explicitly writing the expression for C3n, okay, I mean, n is large. So here I have written 3n, but here I've missed it. So basically, C3n would be pi 3n by 2. I mean, this is the explicit form, right? And even if you take the derivative, so C dash would be some value which is equivalent to Cn by n. Okay, so this is a small n. You could take this to be the degree of freedom, and 3n is basically the number of particles. Sorry, n is the number of particles, and 3n is the degree of freedom, which is equal to small n. And this will be basically some number with this term, right? And when you take the log of this as well, log C 3n, if you like, minus log n, here you have log of 3n minus 2 factorial. So this is going to significantly dominate over log n. So this again is an insignificant term. So even if the system is between energy E plus dE, while calculating the entropy, whether we calculate the volume of the sphere and work with the expression of entropy coming from the volume of the sphere, or we calculate the volume of the shell and from there calculate the entropy and work with it, or if we work with, suppose, calculating the surface area of the shell, right? This is volume of shell and this is surface area, because these are things which are appearing in the exponent, and then you are taking a log and n is extremely large, is working with any of these is practically equivalent with respect to calculating the entropy, because the corrections, whatever will be there, will be order of log n, right? Either order of log n, or yeah. So basically, and what you are really contributing is 3n into either energy or other terms. So these three are equivalent. So we could as well, for the next discussions, work with the volume of a sphere and work with this expression, S equal to kb equal to log omega, and this essentially, these terms, this constant came with respect to the calculation of the volume of a sphere, and n ln v, this anyway doesn't contribute. This was the unit volume of phase space. This was a constant which was 3n by 2. So it looks basically like this, right? And it can be calculated and checked in one. And the energy expression came as 3n by 2 ln 2 me, where E is the energy of the system, right? So we are just rewriting it. So I'm putting this 3 by 2 here so that the prefactor in front of the log terms is n, and thereby I have combined these two terms and written as n ln v e to the power 3 by 2, and this is the constant term. Now I want to write down explicitly the constant term as well, and if we take ln of C3n, right, so then it becomes 3n by 2 ln pi, yeah, which is this expression, minus ln 3n by 2 minus 1 factorial. Okay, and here we are going to use the Stirling's approximation. So Stirling's approximation deals that when n equal to infinity, it tends to infinity, when n is very large, then log n factorial can be written as n ln n minus n. So I'm not going to prove it. It's proved in the appendix of many statistical physics books. But we are going to just use these mathematical results for the rest of the course, right? Because our focus is statistical physics, not derivation of where this comes from. I mean, that would be a separate discussion. It will deviate away. We'll just use this expression. Whenever n is large, we can use ln n factorial equal to n ln n minus n. So this term itself, so ln C3n, we can write it as 3n by 2 ln pi, which is basically this term. And this is being written as 3n by 2 minus 1 ln 3n minus 2 minus 1 n log n. And since it already had minus here, right? So n ln n minus n, here becomes plus and this becomes minus. And of course, compared to 3n by 2, minus 1 is going to be dropped. This is going to be dropped. This is going to be dropped. So we're going to have 3n by 2 ln pi, which is this term, minus 3n by 2 ln 3n by 2 plus 3n by 2 in terms of the constant terms. Okay. If we had h to the power 3n, because that was also what is there here, right? So then there would be another extra ln s to the power 3n. Now, what we are going to do is collect all these different terms together. So basically, this pi comes here. This 3n by 2, right? This 3n by 2. So this had to the power 3 by 2, and it comes with a minus sign. So it is basically 2 by 3n from here, right? And this h cube sits here. And this is n log n. And this is outside log, and this term is here, right? So what have we done? We have again written this where a ln, in front of ln, you have n, and you have 2 pi to the power 3 by 3n to the power 3 by 2, and this is the constant term. The entropy is kb ln this, the constant terms, plus n ln v e to the power 3 by 2, right? And now I have also written here, so that this was n here, and this was again in the constant term n. So it can be easily written s equal to n kb, right? I have combined these terms. So e comes with the exponent 3 by 2. These constants also come with the exponent 3 by 2. And this is v by h cube. And this goes here. All that, so what are we doing? We are rearranging terms. Why are we rearranging terms? So that we can write E in terms of S now. So we had previously written S as a function of E, V, and N. We are rearranging terms so that E is written now. So we are writing E equal to basically taken. So this ln here, right? So it is s by n by kb, and then you take its exponential and so on and so forth. So that's exactly what has been done here. And I also remind you that E we had calculated to be 3 by 2 kBT n, right? Which can be rewritten as n number of moles 3 by 2 RT. Now we have two expressions for energy, which is in terms of entropy, right? And entropy is fixed. I mean, and if we equate these two expressions, if we just equate these two expressions, what we get is, so from here we have v to the power 2 by 3, right? And you have also this exponential term, but that's a constant. That's a constant. So this term is missing actually. So I should really, so this term should also be here, but this is a constant term. Especially, yeah, so this doesn't depend upon energy. But what we can write is v to the power 3 by 2, v to the power 2 by 3 into t, and all the other terms are constant, including this, right? So as long as energy doesn't change, S is not going to change. So as long as if there is a reversible adiabatic transformation, S, E, and N remains fixed, and the above relationship holds. Now, this we have already seen in thermodynamics as well. So remember that this we had got from statistical mechanics. There is KB sitting here, right? And this is also got from statistical mechanics. And as a consequence, we got V to the power 2 by 3 into T equal to constant. Now, I'll just remind you that this 2 by 3 is the same as gamma minus 1, right? Where gamma was Cp by Cv 5 by 3 and gamma minus 1 is 2 by 3. So what we have got is a thermodynamic result of V to the power gamma minus 1 into T equal to constant, but we have got this now from statistical physics. And so if there is reversible adiabatic transformation such that S, E, N, all of these remain fixed, then this relationship holds, right? The other thing is, so let's discuss this relationship also. This was a thermodynamic relationship, right? So can we get it from StatMech? That's the question we are asking. So from thermodynamics, you know that Cv equal to del U del T at constant N and V, which is basically change of energy with temperature at constant N and V. Volume is constant, so if you add energy, pressure can increase. On the other hand, Cp at constant pressure is del H del T, where H is enthalpy, H plus PV, right? So from StatMech, we know that the energy equal to 3 by 2 nkBT, right? And this is fixed. And Cv is, in that case, you can calculate it, take a derivative with respect to temperature, is 3 by 2 nkB. But PV equal to nkBT is also, which I proved, the ideal gas equation, which we got from StatMech, right? We, of course, associated various quantities. We called various derivatives. We associated it with P by T derivative of S with respect to volume. But finally, we had also got this, right, nkBT. And if you calculate H using the thermodynamic relation here, invoking the thermodynamic relation E equal to PV, we have expressions for E, we have expressions for PV. This is 5 by 2 nkBT. Cp, in that case, using this thermodynamic relationship, but we had got this, derived this from StatMech, is 5 by 2 nkB for monoatomic gas, right? In that case, Cp by Cv, again we get as 5 by 3. Right? For monoatomic gas equal to 3 by 2 kBT, which is basically this relation for every degree of freedom. So what are we doing? So we are essentially trying to get various relationships of thermodynamics, which we already know. We have an expression for S, which we said is to be the volume of phase space. And we managed to calculate that. So we have the volume of phase space in terms of E, V, and N. Thereby, entropy is a function of E, V, and N, which I said earlier as well. And taking suitable derivatives, taking suitable rearrangements, and associating Kb log omega with entropy, calling it entropy, and taking suitable derivatives of this Kb log omega with respect to V, with respect to T now, I mean, okay, so T is a derived quantity in microcanonical ensemble. So temperature is something which you get because S is a function of EV and N. So when you take derivative of S with respect to E, that's a condition of thermal equilibrium if two things are brought in contact, and that quantity derivative of S with respect to E, we associate it with 1 by T, right? And we can get out the expression of T with I mean, T is basically E by this 3 by 2 nkb. So that's how we get it. So it's a derived quantity, right? You don't fix it. You don't fix it. You fix your volume, you fix your energy, you fix your number of particles. Till now, we have been discussing ideal gases, but we'll soon move to interacting systems. And from there, so since we have an expression for S, in terms of microscopics, I mean, we started from microscopics, calculated the volume of phase space, got this functional form by integrating over phase space suitably. And from there, we are rearranging terms. We are associating kb log omega with S as a function of these three quantities and getting out thermodynamic relationships. And we see that if we associate S, or rather associate S with kb log omega, things are pretty consistent, at least up till now. So what I want to end the class today is everything till now fits with S equal to kb log omega equation, but using the classical expression. So here, whenever I use this expression, I am using the classical expression for entropy where the particles are considered distinguishable. If they were indistinguishable, I should have used a 1 by n factorial. However, if we decide to live with the classical expression, we still get our PV equal to nRT. We still get our 3 by 2 kBT equal to into n is energy. We still get Cp by Cv equal to 5 by 3. We are still able to get V to the power 2 by 3 equal to T. But there will be a problem arising. And what will be the problem? That's called the Gibbs paradox. And that is the topic of the next class.